So postulates or axioms are statements that are accepted as true without proof. If I said I'm a human, would you need me to prove it to you?
No.
No. But if I said I'm an alien, you'd want proof, right? So I'm a human is a postulate or an axiom, and then I'm an alien would not be. Does that make? Oh, okay. So we had through any 2 points, there's exactly one line. So if I have 2 points, there's only one line that will go between or through those 2 points. Of course, if I help if I actually drew it right. Okay. There's no other line that will connect those 2 points. Through any 3 non-collinear points, there's exactly one plane. So if I have just any 3 non-collinear points and I'm connecting them, it'll be with a plane. And there's only one plane, just like there would all be, like if I took a piece of paper and drew 3 dots on it that are not in a line, that would be, the paper would be the plane. If I brought in another piece of paper and went like this, it's not going to go through the 3 points or the 3 dots. Does that make sense? A line contains, yes, this was another typo. Should have fixed these. Contains at least 2 points. Yes, bless you. At least 2 points. So if there are 2 points required to make a line, and only one line can go through those 2 points, that means every line contains at least 2 points. So if we have a line, just a random line, it's going to have at least 2 points on it. It can have an infinite number of points, but it'll have at least 2. Okay. A plane contains at least 3 non-collinear points. So if I have a plane, there's going to be at least 3 non-collinear points on it, because it takes 3 points to define a plane. So if you have a plane, it has at least 3 points. If 2 points lie in a plane, then the line containing those points is in the plane. So if I have a plane, and if I have 2 points in the plane, so again, there's a piece of paper, I drew a dot, 2 dots on it. If I connect those 2 dots with a line, it's also on the piece of paper. So it's also on the plane. Okay, if 2 lines intersect, their intersection is exactly 1 point. So if I have 2 lines and they intersect, there you go, point. That's the intersection. And then if I have 2 planes that intersect, try to draw this better. Okay, when the 2 planes intersect, they intersect at a line. And that's just like if I take these 2 pieces of paper, you can see that they are going to make a line where they touch.
So those 2 points, that's where you get the line, right?
Yeah, like if this is the plane that looks like it's flat, and then this is the plane that's going down into it, where the 2 pieces of paper meet,
yeah,
that's where the line is.
Can you also draw that same line and draw it diagonally?
Here?
Yeah. No, because it's on the other side.
Well, you know, it depends on how you're looking at the planes intersecting. I suppose you could say this plane was coming down and they were intersecting like this. So it's the way I drew it, there's some interpretation, but if I actually physically had planes, there would only be one line. Does that make sense? Okay. So I'm going to go back to the original one that I put. Okay, so what we do is, now this is a very bad rendition of a photo that was in the book. This is a building. This is another building, and that's like the side wall of the building going back. Can you tell? Yeah. Okay. It's like a triangular building. Okay, so if line M contains points F and G. Okay, so here's line M, F and G. Oh, that should be an S. Okay, so we're going to say which postulate makes this true and how the picture shows that. So we have line M contains points F and G. Point E can also be on line M. Okay, so this is line M. We can see that point E is on line M. And the postulate is that each line contains at least 2 points. But it contains more than that. So we can use that postulate to say that yes, line E can be on this, or point E can be on the same line because the line has at least 2 points, not a maximum 2 points, right? Okay, lines S and T intersect at point D, so we see here's line T, here's line S, there's point D, so we can see this. And the postulate that states that true is that 2 lines intersect at a point. Okay. Points A, B, and C determine a plane. A, B, and C. The way we know that's true is that 3 non-collinear points determine a plane. And then planes P and Q, so here's plane Q, here's plane P, are intersecting at line M. And that's 2 planes intersect at a line. Looking at this packet, we're going to look at the picture and see that we can see this. And then we're going to say which postulate makes it true. Okay, so what we have is that planes O and M intersect in line R. Here's plane O. There's O. Here's M. And here's their intersection. So we can see that that's true. And the postulate is that 2 planes intersect in a line. If we look at line P lies in plane N. Well, here's plane N, and here's line P. If you look on your paper, you can see the P. I accidentally cut it off when I brought it over. So here's line P. If you look at this, we have points A, E, and D. They're all part of plane N because they are on the corners of plane N. So they're all on plane N, and we have the postulate that says if 2 points lie on a plane, then the line containing them is also on the plane. So that would be the postulate for this. So it's true. So these are both true.
But where's P?
It's on that, if you look on your paper, it got cut off on the picture. So the blue one was line P. So we can see that they're true looking at the picture, and then this is the postulates that shows us that for sure it's true. These postulates, we accept them as true, so here they are. All right, sometimes we have things that are always true. For example, a line has at least 2 points. That is always true. Sometimes we have things that are sometimes true. For example, I use an umbrella when it rains is sometimes true and sometimes not true because I forget the umbrella. And then we have things that are never true. For example, I frequently fly with my big giant wings that I have right here. That's never true, right? I don't have any wings, so I don't go flying. So we need to look at things and we need to decide if it's sometimes true, always true, or never true. Always true, these are just sort of facts. And sometimes is situational. You know, like, for example, the umbrella. Sometimes I have an umbrella when it rains and sometimes I don't. When I have one, I use it. When I don't have one, darn, I get wet, right? So these are situational. So we have, if two coplanar lines intersect, then the point of intersection lies on the same plane as those two lines. Okay, coplanar. That means we're on the same plane. Okay, so if I take a piece of paper to represent my plane. Oops, that wasn't pretty. Okay, here's my plane. And if I draw two lines on it intersecting. Okay, so on our piece of paper, our flat piece of paper, we've taken a marker and we've drawn two lines and they're intersecting. The point where they intersect, is that going to be on that same piece of paper?
Wait, what?
If I take a piece of paper, hold on, let me pause this for a second. Because the two lines are on the paper that represents our plane, where they intersect is also on that paper. So this isn't always. It can never not be on the paper if the lines are on the paper. We can't intersect like off in space if we're on the paper. Okay. 4 points are non-collinear. Well, let's think about that. If I draw my 4 points like this, they're non-collinear. But what if I draw them like this? If I draw them like that, I can draw a line through them. So this one is situational. It depends on where the points are. So this is sometimes true. Okay. Two lines. This one? Yeah, because 4 points can be on a line together or they can not be on a line together. So sometimes it's true and sometimes it's not. It depends on which points we're talking about. Okay, so if we're talking about these 4 points, true. We're talking about these 4 points, false.
Oh, no.
Right, so, okay, two lines determine a plane.
False.
Well, we have, well, let me do this. We have our X and Y axis that you guys are used to seeing, right? That determines a plane. Because it makes our coordinate plane. We can, if the two lines are going to go on forever and ever and ever, and then there's all these points along them, they make a plane.
Okay.
But if I had, say, one line here and another line up here, do these necessarily make a plane? Here, let me use the markers. Like if I had like this and this, do these necessarily make a plane?
Yeah.
They could. There could be a piece of paper that goes like this through them, right? But what if they're like this?
They got different directions.
Is that going to make a plane? No. So this one, so if I have a one line that goes flat and another line that goes like this, but this one is also sometimes true. Because it depends on which two lines we're talking about. If we're talking about two lines that are parallel or intersecting on the same level, yeah, that's a plane. But if I talk about two lines that are what we call skew, they never intersect, but they're not parallel, that's also sometimes true. But skew is where you have lines that never intersect, but they're not parallel. Like these two markers that are facing opposite directions. Those will never make a plane. So it depends, again, which lines we're talking about, whether this is true or not. So this is sometimes true. And then three lines intersect in 2 points. That's 3. That's 1. That's 2. Well, it's saying intersect in 2 points. This is 3 points. This is 1 point. This is 2 points. Sometimes true. I should have given you an example of a never true. Hold on one second. Okay, so 2 lines intersect to form a plane. Here's one line. Here's another line. They're intersecting. Is that a plane?
Yes.
The intersection.
Oh, no.
No, the intersection is a point, right? So this is never true. Because our intersection is a point. Something else, like we could say that.
What if the line had this line had like 2 other points, and it would
Well, there could be points on the 2 lines that then could define a plane, but I said they intersect to form a plane. The intersection doesn't form a plane. The intersection forms a point. They intersect at a point. Parallel lines share 2 points. If I have parallel lines, can they share anything? No, because they never meet, right? So this is another kind of a never true. Right? So if we come back to our examples, decide if these are sometimes, always, or never true. On number 3, the definition of the plane is that 3 non-collinear points determine a plane. That was our postulate. It was 3 non-collinear points. So there can be 3 collinear points on the plane, but 3 collinear points don't determine a plane. Does that make sense? So they have to be non-collinear to determine or define the plane.
For number 4, when it labeled the points A and B, that threw me off because the points could be like labeled anything.
Well, that's true, but if I have a point A here and I have a point B here, there is a line that exists that can go through them. So that's always true that there's a line. Now, whether we draw that line or use that line is up to us, but the line exists. Does that help? Number 5 is sometimes true. Because sometimes the plane has 3 lines and sometimes it doesn't.
I thought 4 would be sometimes true because a line can be determined by center, like.
Well, the definition of the line, remember we said our postulate says that any 2 points have exactly 1 line going through them. So there is a line that goes through these points. It always exists. We may choose not to use it, but it's always going to be there. Does that help? Okay. Okay, so paragraph proofs. Paragraph proofs are considered to be informal. And, like you guys are all being informal right now. Formal would be, you put on your tuxedos, you put on your fancy dress, your hair, your makeup, and everything. And today you're informally wearing jeans or whatever. So these are informal proofs. These are like the jeans and t-shirt proofs. Okay. A theorem is a statement or conjecture that has to be proven. Okay, so before when I said my postulate is I'm a human, and you all accept that as true, I'm human. But if I say I'm an alien, before you would believe that, I would need to prove it to you. The theorem would be I am an alien. And then the proof would be whatever process we decided would be enough to prove it for you. Maybe I have special powers and I can levitate things, or maybe you guys want DNA testing, or, that's to be determined. So for the proof, we start by listing the given information. There will always be given information. If there's no given information, you can't prove it. Okay? If you have not been given a picture specifically, you should draw one based off of the given information, because drawing the picture will make things much, much easier, because you can draw it, label it, look at it, see, physically see what's happening. Okay. The statement, or step 2 is to state the theorem or conjecture to be proven. Okay. So we want to tell what it is that we're trying to prove. Step 3 is to create the deductive argument. Okay. We're going to form a logical chain. Okay. So we take the given information and we take the theorem, and then we create a deductive argument going from our given information to our theorem. Okay. Step 4, we're going to justify each statement with a reason. Okay. Reasons. these are definitions. Properties. Postulates. And any theorem that has already been proven. And then step 5 is we state the proven. Okay, so on the reasons, I can't use any theorem that hasn't been proven. So if I was trying to prove to you that I was an alien and I was going through this list of deductive arguments, and there was another theory that I had that said aliens have pinky fingers that are 2 inches long or something. That's just like another theorem. I can't use that theorem to try to prove that I'm an alien. Because I haven't proven that aliens have pinky fingers that are 2 inches long. Does that make sense? So I can't use something that's not proven to prove something else. It has to be an already proven theorem. Okay, so the paragraph proof is an informal proof. We actually write a paragraph. Okay, and we're explaining why our conjecture is true. Okay, and it's called an informal proof, but informal is still valid. Okay, so it's not invalid because it's informal. It's still valid. Okay, so here we have, given that M is the midpoint of XY, write a paragraph proof to show that XM is congruent to MY. Okay. So I write down given. Okay, that's my given. M is the midpoint of XY. And I want to prove that XM is congruent to MY. Okay, so I'm going to try to get from M is the midpoint to that makes these two parts congruent. Now I'm going to draw a picture. Here I have X and Y, and M is the midpoint. Okay, so I've got this picture. And then I'm going to write my paragraph. Okay. Okay, so I'm saying if M is the midpoint of XY, then we know that XM is equal to MY from the definition of midpoint. Okay. This is a statement. This is a reason. Okay, my statement is that XM is equal to MY. My reason is it's the definition of midpoint. Okay. All right, then from there, I can say that since XM is equal to MY, that makes XM congruent to MY from the definition of congruent. Okay, again, this is a statement. This is a reason. So I'm making a statement, giving a reason, making a statement, giving a reason. And then I just got to my proof part. XM is congruent to MY. So thus XM is congruent to MY. Period. The end. That's what I've proven. I have C is between A and B, and AC is congruent to CB. So I want to write a paragraph proof to show that C is the midpoint of AB. So I'm basically going backwards on this one. I'm going the other direction, right? So in this first example, I said, ooh, I have a midpoint. I want to prove that that makes the two parts congruent. Here I have a point between them and two congruent parts. So I want to prove that it's a midpoint. So what I've been given is that C is between A and B, and AC is congruent to CB. Those are both given. I want to prove that C is the midpoint. Okay. So draw a picture. Okay. I've been given this information. So I know that these two lengths are the same, so I can draw that on the picture. Right, so I can say if C is between A and B, and AC is congruent to CB, then AC is equal to CB from the definition of congruent. Okay, so I'm saying that if these given things are true, so if AC and CB are congruent, then that means their measures are equal from the definition of congruent. So this is my statement. Here's my reason. Okay, and then I can say if AC equals CB, then C is the midpoint of AB by the definition of midpoint. Okay, statement, C is the midpoint, reason, definition of midpoint. And then I can say thus C is the midpoint of AB. So we've proven it. We used facts that if they're congruent, that makes their measure equal. And if the two measures are equal, then that makes it a midpoint. And we used definition of congruent and definition of midpoint to get there. Is proven true. Can only has one A. Okay. Once it's been proven true, it can be stated as a theorem and used in other proofs. So we've now proven from both directions, right, that if we have a midpoint, it gives us congruent segments, and we've proven that if we have congruent segments, it gives us this midpoint. So by doing that, we can now use the midpoint theorem, which is that if M is the midpoint, of AB, then AM is congruent to MB. Okay, and the picture for that will look like this. Okay, so now we have this theorem, we have proven this theorem, so now in future proofs you can use midpoint theorem. So you don't have to go through definition of midpoint, definition of congruent, definition. You can just say this because of midpoint theorem. When you're going through the proof process and you're given those initial given statements, so you start with given, right? The next thing you want to think to yourself, what does this mean? Okay, I've been given that angle A and angle B are complementary angles. Okay, what does that mean? Well, it means that angle A and angle B add up to 90. And then once you've figured out what it means, like, how can I use that? Okay, so angle A and angle B add up to 90. Maybe I'm trying to prove that two lines are perpendicular. Well, then I can use the fact that these two angles are complementary, means that they add up to 90, which makes them a right angle, and right angles mean perpendicular. Does that make sense? So like you want to think about what things mean and then how you can use them to get to the next step. Before we start proving, we want to figure out what the reasons are, or the postulates. So if I'm looking at this picture, I have DG and DP are in plane J. H lies on DG. So here we go, DG, DP, plane J. Or is that an I? Oh, whatever that is. And there's H. And we want to state the postulate, just the postulate. We don't have to prove anything, but we want to state the postulate that would make these true. Okay. So looking back over the postulates, what do you think for this one? Anybody? That's a good thought. Okay. So they don't look collinear because they're not on the lines that we have, but I can create a line through those. Yeah, you can. Because we have a postulate that says there's exactly one line through any 2 points. Or any 2 points have exactly one line going through them. I don't remember how I originally said that, but
it's not there.
But it doesn't have to. Okay, so the postulate, the exact words of our postulate were through any 2 points, there's exactly one line. Okay, so just because they didn't draw the line, if you have 2 points, you can put a line through them. Whether it's there right now or not, it does exist. Kind of like that. Like, my dog is not here right now, but she still exists. Like, this line wasn't there right now, but it still exists. So anytime you have 2 points, you can have a line. That's what the postulates are. They're like anytime these things happen. So anytime you have 2 points, you can have a line. Anytime you have 3 points, you can have a plane. Okay. Points D, H, and P are coplanar. And that postulate stated exactly is through any 3 non-collinear. So we have D, H, and P, non-collinear points, there is exactly one plane. Okay, these two are those kind of things that are always true. 2 points will always have a line. 3 non-collinear points will always have a plane. Whether the plane is in the picture, like whether you currently see the plane or not, is different, but that always exists. Okay?
So it's planar, meaning the 3 points are anywhere in the plane?
Yeah, they're in the plane, yeah. Okay, so we're going to try to write a proof. So in the figure at the right, point B is the midpoint of AC, and point C is the midpoint of BD. So what we have is our givens. By the way, you should always be able to come up with at least the given part of a proof because it's been given to you. So we have point B is the midpoint of AC, and point C is the midpoint of BD. Okay, so those are given. And we're trying to prove that AB is equal to CD. Okay, so what we're trying to prove, we're trying to prove that this length right here is equal to this length right here. Okay. What we have is point B is the midpoint of AC. Okay, what does that tell us? We have that new midpoint theorem we can use, right? So then I can say then AB is congruent to BC by the midpoint theorem. Okay, so that's our first given, and that's what it means. Okay. Our next given statement is if point C is the midpoint of BD. So we have another given, and what does it mean? It means that BC is congruent to CD by the midpoint theorem. Okay. Now let's stop and think about this for a second. We have AB is congruent to BC, and we have BC is congruent to CD. Where do you think we can go with that?
AB is congruent to BC, and BC is congruent to CD, then AB is congruent to CD.
Perfect. Yes. So since, let me do that blue again. Okay, we have since AB is congruent to BC and BC is congruent to CD, then AB is congruent to BC. Do we know why? This is technically the transitive property.
You showed us that property?
No, but you could use law of syllogism. Because remember, we have law of syllogism is if P is Q and Q is R, then that makes P R. So why don't we use that one? Because that's what we've used so far. So by the law of syllogism. Okay. Now we've got them congruent. AB is congruent to BC. But we're trying to prove that they're equal.
Should that say CD instead of BC at the end?
Yes, it should. Thank you very much. Too many letters. Okay. So our last sentence is since AB is congruent to CD, that makes AB equal to CD by definition of congruence. And we've proven it.